All right. So today we're going to talk about randomization of spontaneous broken gauge theory. So this is part one. In part one, we'll just describe the Goldstone theorem and the so-called arc-psi gauges, which are gauges for the quantization of spontaneously broken theories. And in part two, next lecture, I will talk about the quantization and randomization per se. Let me note that the exercises end this lecture, so I only have exercise for this lecture, and the next two lectures don't have exercises. And also to note, as I told you, that the final lecture will be on Friday at 10 a.m. since nobody complained about this. And that would be a lecture on pseudo-Goldstone bosons. All right, so the Goldstone theorem. I already mentioned it. The Goldstone theorem says that whenever there's a spontaneously broken continuous symmetry, we find massless states called Goldstone bosons. The proof is rather simple. So let's consider a general Lagrangian of the type some kinetic term that depends on derivatives on the fields and potential for the fields. And let's consider the minimum of that potential. So the place where the derivative of the potential with respect to the fields is 0. And then let's expand the potential around it. So let's write it as the potential at that point, phi 0, plus the quadratic piece, so 1/2 phi minus phi 0a, phi minus phi 0b, and d2 d phi a, d phi b of v at the point phi 0, plus higher order. So this is the quadratic approximation. And then, as we saw, we can define the second derivatives, so d2 of d phi a, d phi b of v at phi 0 to be the mass matrix, so m squared ab. And let's consider a continuous symmetry that changes phi a into phi a plus a small parameter alpha times some quantity delta a that depends on phi. So, well, I mean, for a linear symmetry, I would say T capital A in the representation R times the matrix T, with indices AB, phi B. But let me be more general and write like this, just delta A. In the particular case that phi A is constant, so meaning that it's independent of the space-time coordinate x, then having the Lagrangian be invariant means, since the kinetic term depends only on the derivatives, which are 0 now, the potential is invariant, that means the Lagrangian reduces to the invariance of the potential, to the fact that v of phi a is it's equal to v of phi a plus alpha delta a of phi. Another way of saying that is that taking the derivative of the potential with respect to phi a, so dv d phi a, and then multiplying with the variation of the fields divided by this small parameter alpha, so delta A of phi, at the point phi 0 is equal to 0. Now, taking a second derivative on this whole equation, so dd phi b on this, we get that d delta A with respect to phi b at phi 0, dv d phi A at phi 0, plus, acting with the second derivative on the potential, delta A of phi 0 plus, times d squared d phi A d phi b v at phi 0. This is equal to 0. But the first derivative, was 0, since phi 0 was by definition the minimum of the potential, right? dv d phi 0 at phi d phi A at phi 0 was equal to 0. So this is 0, and that means that we have only delta A of phi 0 times the second derivative of v with respect to phi A phi b, and phi 0 is equal to 0. Now, from this equation, there are two possibilities. One, that delta A at phi 0 is equal to 0, which would mean that the symmetry leaves the vacuum invariant. So the symmetry is such that phi 0A is invariant. This is not the situation we're interested in. This would mean that the vacuum is not spontaneously broken. But if there is spontaneously breaking, then delta A of phi 0 is non-zero, which means that the product of delta A phi 0 with this second derivative with respect to phi A and phi b, which by definition is called the mass matrix m squared AB, is equal to 0. Another way of saying that then is that there is a 0 eigenvalue for the mass matrix in the direction of the symmetry, in the direction delta A. And this 0 eigenvalue for the mass matrix is called the Goldstone boson, is the massless mode associated with the spontaneously broken symmetry. So that's the Goldstone theorem, very simple. However, what we wrote until now was at the classical level. What's more interesting is to show that the same thing remains true at the quantum level. So quantum corrections don't spoil this property. So we can repeat the same procedure, but in order to consider the quantum corrections, then we have to consider not the action, but the effective action, the quantum effective action, gamma. And we've considered constant fields phi A, which means that then that the effective action becomes just the effective potential. Or rather, the effective potential times minus the volume of space-time, so minus v times t. But if there are no quantum anomalies, the effective potential respects the same symmetries as v. So we can just trivially repeat the same argument above for the same symmetry. So then we obtain that in general, this second derivative of the quantum effective action gamma with respect to phi A and phi b at some momentum squared p squared that is different than m squared, so off shell, is 0. And if you consider the particular case of 0 momentum or constant fields, constant classical field, that would be equivalent, then gamma becomes this effective potential times minus Vt, So we have that the second derivative of the effective potential with respect to phi A, phi B is 0, as we expected. Yeah, all of this is times delta A of phi 0. So, yeah, where was this? Let me see. This was. Yeah, so this was times m squared. Sorry. This is times delta A. All right. So let's consider the abelian case for the R psi gauge. So the simplest case, then we'll generalize to the case of interest, which is the non-abelian R psi gauge. So if we have a gauge theory that is not spontaneously broken, the Lagrangian in Minkowski space for the gauge field and ghost, for the gauge fixing and ghost is minus 1 over 2 psi g squared minus b del g d alpha c. So g is equal to 0 is the gauge condition, and well, psi or alpha is well, I call it psi because I called alpha the parameter, but psi or alpha before was the final parameter. And then the variation with respect to the gauge parameter of the gauge fixing condition gives the kinetic term for the B and C ghosts, right? So for the gauge transformation, that's delta A mu is minus d mu alpha, and delta phi is minus e alpha phi, or the usual gauge field plus complex field. For the covariant or Lorentz gauge, where G is d mu A mu, the kinetic term for the BC ghosts is the variation of the gauge condition with respect to the parameter. So, so here I have del mu of delta A mu, which is minus d mu alpha, but I do the variation with respect to alpha, so I get a minus del squared. Now, going to the spontaneously broken case, where the complex field in terms of the real and imaginary parts is phi 1 plus I phi 2 over square root 2. And then phi 2 is called this curly phi. And phi 1 is the Vev V plus the Higgs H. And curly phi being the Goldstone boson. Then we choose the gauge condition to be, instead of just d mu a mu minus psi ev phi curly phi. So this is what is called the arc psi gauge. And we note that this is just a continuation of the Lorentz gauge, because if I put v equal to 0, going back to this non-broken case, will reduce to the Lorentz gauge. Let's compute then the expansion of the kinetic term for the complex field phi. So the covariant derivative is del mu minus I e a mu as usual. So then the covariant derivative d mu on complex field phi becomes 1 over square root phi, 1 over square root 2, del mu h, well, del mu v is 0, and then oops, somebody wants to get in. All right. Then minus I e a mu phi reduces to one component. So the imaginary component becomes e curly phi a mu, and then the imaginary component is I del mu phi minus e times the real component of the field, so v plus h times a mu. So then the kinetic term minus absolute value d mu phi squared is, well, this squared plus this squared, which amounts to this. So minus a half d mu h squared, which is the kinetic term for the Higgs, minus a half del mu curly phi squared, which is the kinetic term for the Goldstone boson, then minus e squared over 2 v squared a mu, which is a mass term for the gauge field, plus ev a mu del mu phi curly phi, which is the mixing between the photon and the Goldstone boson, and plus e a mu h del mu phi curly phi minus curly phi d mu h, minus e squared vh a mu, minus e squared over 2 h squared plus v squared a mu. Yeah, right. So these are interacting terms, all of them. So the second and third line. The second line is cubic in the field, and the third line is quartic. No, sorry, it's also, there's a cubic term here and then a quartic term. Then also I can expand the potential, lambda over 2 absolute value phi minus v squared over 2 everything squared, as a mass term for the Higgs, lambda v squared over 2 h squared, plus cubic interaction, lambda v over 2 h a squared plus curly phi squared, plus a quartic interaction, lambda over 8 h squared plus curly phi squared. I can expand also the gauge fixing term as minus 1 over 2 psi d mu a mu squared. So that's the usual gauge fixing term in the unbroken theory, minus psi e squared v squared over 2 curly phi squared, so that becomes a mass term for the Goldstone boson, plus ev curly phi v d mu a mu, a mixing Dalton boson gauge field. And then for this mixing, I can partially integrate this term into this, so the derivative onto the Dalton boson. So I get minus EV A mu d mu Li phi. So the mass term for curly phi is, you see, minus psi e squared v squared times curly phi squared over 2. So this is the mass squared, meaning the mass of the Dalton boson becomes square root psi ev. But since ev is the mass of A, yeah, here. So minus a half EV squared times A mu squared. So the mass of A is EV. The mass of the Dalton boson curly phi is square root of psi times the mass of A. And we also see that the mixed term will cancel between the kinetic term and the gauge fixing term. So in the kinetic term, we had this mixing, and in the gauge fixing term, we had the corresponding term with a minus sign. So these two terms cancel against each other, which is part of the reason why we chose the gauge fixing term to be the one we chose. So this arc psi gauge was chosen for this reason. Okay, so remember that the gauge fixing term, in the absence of the spontaneously broken correction, like psi, would have been just this. So now we've added this term that cancels the mixing. So in the in the case of the unbroken theory, we had this mixing, which we removed by redefining the gauge boson to A prime mu. And what we said in words was that the gauge boson eats the Dalton boson to become massive. All right. But now this mixing term cancels out, and we get the mass for but the Dalton boson still gets a mass, which is square root of psi times MA. All right, then let's go to the ghost term. The gauge transformation around the Higgs vacuum is as follows. So the field phi, as you remember, is V plus H plus curly phi over square root 2. And then delta mu is minus d mu alpha. But then delta phi, let's go here. So sorry, here there's an I missing, right? Yeah. So we had this transformation law. Delta phi is minus I e alpha phi. But now we write the real and imaginary parts of this equation under this expansion. And correspondingly, we get that from the real part, we get that the real part of the variation, we get that the variation of the Higgs is plus alpha, plus E alpha times the Dalton boson. And the variation of the Dalton bosons is minus E alpha V plus the Higgs, the Vev plus the Higgs. So now you see that in the variation of the Dalton boson, we get this constant piece. So the variation of the Dalton boson is not a linear. So this symmetry in all is not a linear symmetry anymore. Normally, linear symmetry means that the variation of a field is proportional to the field, to another field, to some field. But now you have this constant piece, so we say this is nonlinear. And then the kinetic term for the ghost is B. So the kinetic term for B and C is given by the variation of the gauge fixing condition with respect to alpha. So the gauge fixing condition is d mu a mu minus psi EV times Goldson boson. And we vary this with respect to alpha. And from here, you get minus d mu, so minus del squared. And from here, we get minus psi EV times the variation of alpha variation of Goldson boson divided by alpha, which is minus EV plus H. So all in all, plus psi E squared V times V plus H. So then the ghost term is minus B times this object times C. And then we can partially integrate one of these derivatives onto B and write minus d mu B d mu C. Then this term, the middle term, becomes mass term for BC. And then the last term is an interaction between the Higgs B and C ghosts. But from here, we see that the mass of the BC ghosts is square root of this, so square root of psi times EV, which is again square root of psi times the mass of A. And finally, let's go to the kinetic term for the gauge boson A mu. So the kinetic term is, as usual, integral of minus f minus squared over 4. But we also have a term from the gauge fixing term. So excuse me. So from the kinetic action, we get the usual minus 1/2 A mu times d mu d nu minus g mu nu del squared times A nu. And then from the gauge fixing term, it's minus 1/2 A mu times the mass squared ma squared g mu nu times A nu. And then also we get this minus d mu d nu over psi term, where we just partially integrated. So we had this term. And then here, here I wrote it partially integrated. So I partially integrated this derivative onto this field and this derivative onto this field. So I have d mu a nu times d mu a mu, which is written then like this. Okay. So I have this kinetic operator. And of course, derivatives are complicated, so it's easier to go to momentum space. And then this object becomes in momentum space minus 1/2 A mu tilde, or Fourier component, of minus k, and to the right A nu tilde of k. And then in here I'll get so the derivative is replaced with minus I k mu. So d mu d nu becomes minus k mu k nu. And then I have also this component with minus 1 over xi for the same thing. And then with g mu nu, I have these two terms. So minus del squared becomes k squared. And plus m squared remains plus m squared. So this is the kinetic matrix that we need to invert in order to find the propagator of the gauge field, and correspondingly also the masses for the various modes. So what we'll do is we'll use the projectors p mu nu of k, which is g mu nu minus k mu k nu over k squared, and k mu nu of k, which is k mu k nu over k squared. Now, these are projectors onto subspaces. So whenever I have two projectors onto two subspaces that are complete in the higher space, so the one subspace plus the other subspace equal the total space, the conditions we have are that the projectors obey the condition that the square of each projector is the projector itself, right? So once we project, there's nothing to project anymore. If we project another time, where we just do back to the same thing. The projectors are orthogonal. So we have p squared equal p, k squared equal k. The projectors are orthogonal, so p dot k is 0. So the subspaces that correspond to are also orthogonal. And the subspaces are complete in the total space, meaning that the sum of the p projector and the k projector is the identity. And we can easily verify this thing. For instance, p dot k is 0 is the easiest to see, I suppose, because this has both k mu and k nu. So either one of them, so let's say I multiply this by k mu, or by k nu is the same thing, by k mu, then I get k squared here, cancels with k squared, and here I get k, and then I get k nu minus k nu. So that's clearly 0. And you can check that the square of this is equal to the thing itself, the square of this equal to the thing itself, and that the sum of both is the identity. Indeed, the sum of both means this cancels with this and get just g mu nu, which is the identity in the vector space A mu. Okay? All right, so these being projectors onto subspaces, so then I can write the kinetic operator in this way in terms of the projectors. So k squared plus m squared times, so as you can see, g mu nu appears here and appears only in p mu nu. So this is k squared plus m squared times p mu nu. And then the remaining stuff must form something with k mu nu. So it's k mu nu of k times 1 over xi k squared plus xi ma squared. So xi with 1 over xi cancels, then you get ma squared k mu nu. But if I write it like this and use these conditions obeyed by any two projectors which are complete, mean that I can easily write the inverse, so the propagator, as the propagator delta tilde mu nu of k as p mu nu of k divided by k squared plus ni squared. So basically just invert this scalar part. And here as well, invert this scalar part. So xi over k squared plus xi ma squared times the same k mu nu. So the reason is simple. So now we see P and K are transverse, so I can, when I multiply this with this, I basically I multiply just the parts with P mu, but then this cancels this, and P times P is P, and here this cancels this, but K times K is K, and then I'm left with P plus K, which is the identity. So indeed, this is the inverse of this. All right, but now let's look at this propagator. So this is the sum of two propagators. So there are two modes in here. There's the transverse, this propagator P mu is transverse, meaning multiply with K mu or K nu gives 0. So that's the transverse part is the physical part of the propagator that has mass ma squared. And then there's this unphysical part that's proportional to K mu and has mass psi times ma squared, right? Mass squared psi times ma squared. So mass square root of psi times ma. All right, so now in total, then, so we wrote the kinetic terms for everything, for the scalars and for BC and for A mu, which is divided into transverse and longitudinal part. So the part corresponding to K mu is called longitudinal or unphysical. And we saw that all 4 unphysical modes, which are the Goldstone boson. Why it's unphysical? Because as we saw in the previous lecture, the Goldstone boson is eaten by the gauge field, which after that becomes massive, right? So we're doing an expansion in arc psi gauge, but in principle, I could have used, as before, the Lorentz gauge, right? So the theory is supposed to be the same. So the physical modes are supposed to be the same. And indeed, the physical modes are the Higgs and the photon, which has become massive. Okay, so the transverse photon is massive, as before, with the mass ma. But the unphysical modes in the arc psi gauge are such that they all have the same mass, square root of psi times ma. These are the Goldstone boson phi, which was, it's unphysical because it was eaten in the previous description, the Gauss BC, and the longitudinal photon. And so writing things in arc psi gauge, or writing quantum theory in arc psi gauge, means that in loops, we have we can have the physical modes, the Higgs and the massive photon, the transverse massive photon. But we can also have the unphysical modes, the Goldstone boson, the quartet, the Goldstone boson, B and C ghosts, and the longitudinal or unphysical photon. And but all of these unphysical modes have the same mass, which makes it easier for loops of these unphysical modes to cancel. And that is the reason why the arc psi gauge is interesting, because it makes it obvious that there is a cancellation of loops of unphysical modes, such that the theory makes sense. All right. Another observation is that if I put psi equal 1, which is the equivalent of the Feynman gauge for the unbroken theory, Feynman gauge meaning you remember, is not a gauge really, it's just a choice of gauge fixing term. But for that choice, if I put psi equal to 1, the parameter that before for the unbroken theory was called alpha, then I get this, that this delta tilde is just g mu nu over k squared plus ma squared. So if psi equal to 1, I get this is 1, and then the common denominator k squared plus m squared, and then p mu nu plus k mu nu is just g mu nu. And this is just the Klein-Gordon propagator times g mu nu. So for a scalar mode, which is the same thing as we had in the unbroken theory. However, so while this choice is nice, we will continue to use the arbitrary psi in order to see the psi independence of physical quantity in order to test our calculation, and also to see that there's this quartet of unphysical modes which have different, a mass different than the physical modes, but equal among each other in the quartet. All right. So to conclude, we have to conclude this part, we have the propagator for the Higgs. We have 1 over k squared plus mh squared, where the mass of the Higgs is square root lambda times v. The would-be Gaussian boson, which is now unphysical, has the scalar propagator 1 over k squared plus psi ma squared, which is the same as the propagator for the Gauss B and C. And the vector has the propagator delta tilde mu nu of k, where the mass of the transverse or physical part is EV, and the mass of the unphysical or longitudinal part is still square root of psi times ma. Then about the interaction part, if I put together all the interaction terms, we find this form of the interactions. So this cubic term, then this quartic term, then this cubic term that depends on derivative or momentum, another cubic term, another quartic term, and cubic term with the ghosts. All right, now let's go to the non-abelian case of the arc-psi gauge. The generalization now is rather simple, since we have seen how to generalize spontaneous symmetry breaking to the non-abelian case in the last lecture. So the gauge fixing and ghost part of the Lagrangian are also of the type -1 over 2 psi, now GA, because the gauge condition has an index now. It has a gauge index is GA, and then the ghost term is -BA times kinetic term variation of GA with respect to parameter alpha b times CB. And the gauge covariant derivative is d mu is del mu plus g a mu a ta. And we expand around the VEV for phi I, which is called VI, as phi I is VI plus chi I. So this is a generalization written with a single index. So before we had written specifically the Higgs H plus I times the Wilson boson curly phi. But now we write with an index chi I. And then the gauge condition for the arc-side gauge is the Lorentz gauge with an index, so del mu A. Then minus psi G, the coupling, times TAIJ VG chi I. Right? So before we had V times times the equivalent of chi. Okay, so then the gauge fixing term becomes the usual Lorentz gauge, non-abelian Lorentz gauge, minus 1 over 2 psi del mu A squared. Then this mixing term between chi I and A mu A. So psi G TA ij Vj times the mixing chi I del mu A minus this mass term for the chi's, psi G squared TA ik Vk TA JL VL times chi I chi j. And then, as before, I partially integrate this derivative onto chi, as in here, and then I can also, for use in the kinetic operator, I can partially integrate the both derivatives in the normal term. So this into here and this onto here, as in getting the term in here. So minus half 1 over 2 psi del mu A nu A times del nu A mu A. So this term then is the mass matrix, right? So it's psi times m squared ij. So psi times g squared TA ik vk TA jl vl. Note that writing it like this means we use the convention where the generators are anti-Hermitian. So TA dagger is minus TA. So then from the kinetic term for the scalars, minus a half d mu phi I dagger, d mu phi I, we get the kinetic term for chi I, minus a half del mu chi I del mu chi I. The mass term for the gauge field, so minus g squared over 2 TA ik dk tb il vl a mu a b mu. The mixing term between a mu and chi I, gta ik vk a mu a del mu chi I. And then interaction terms. So G A mu A chi I TA ij del mu chi j minus G squared A mu B, this constant TA ik vk tb ij times chi j, and then a quartic term minus G squared TA tb ij chi j A mu B. And again, we can see that canceling between the mixing term between the vector and the would-be Golson boson. This one cancels with where it is, this one, which is the reason why we chose the arc-side gauge in this way. Well, one of the reasons, as we said. And the ghost term is obtained by considering the gauge transformation on the fluctuation divided by the fluctuation. So A mu goes to mu A goes to mu A minus d mu A B alpha B, and chi I goes to minus G alpha A T A I J V plus H. So then the variation of GA with respect to alpha B is minus d mu from the normal part, from the part corresponding to unbroken theory, minus d mu times the variation, sorry, d mu times the variation of mu A was divided by alpha, so minus d mu AB. And then the term with psi is this term divided by alpha A times, so the arc-psi gauge is minus psi times GA, TAIJ, VJ times chi I. So now I vary chi I get this thing and divide by alpha A, and then I get plus psi G squared TAIJ, VJ, TAIL times V plus chi L. Okay, so then I can divide this into a term with VL. So this term now is a constant, and this term is a term with chi L. And this, but then this term comes in between, in the action in between a B and the C, with a minus in front. And you see then that this constant piece in between minus B and C acts as a mass term. So this is a mass matrix. So the mass matrix m squared within this is AB is given by this for the mass matrix for the B and C. And then this is an interaction term between BC and chi L. Okay, so I've written well, not all the terms, but to this I should have added also the normal kinetic term for A mu, so minus a half F mu A squared, minus a quarter F mu A squared. And then we see that as before, as we said, that the mixing between the vector and would-be Goldstone boson cancels. And then I have the same mass terms for the Goldstone, the would-be Goldstone boson. The same mass matrix here, psi G squared TA IK VK TA JL VL. It's exactly the same mass matrix as in here. So the would-be Goldstone boson and the BNC ghosts, and also this thing appears also in the mass matrix for A mu in here. Yeah, this is a little bit less obvious, but so it doesn't appear with psi, but remember it's the same issue, that the same thing that we obtained in here. So we get ma squared times g mu nu, but then when I write it in terms of physical and unphysical modes, the unphysical mode will have a psi in front. So as in the abelian case, we have a quartet of would-be Goldstone of unphysical modes, the would-be Goldstone boson, the BC ghosts, and the longitudinal part of the gluon, that all have masses, equal masses, and given by this thing times square root of psi. And the longitudinal part has the transverse part of the gluon gets a mass proportional to without proportional to this thing, but without square root of psi. So exactly the same theory, the same thing as in the abelian case. All right, so this is what I wanted to tell you today. Do you have any questions? Can somebody check that they can still hear me? Okay. So if you have no questions, then I'll see you on Thursday at 9. And as I said, I will also have the last lecture on Friday at 10 a.m. So these next two lectures will be lectures without exercises, and then since next week there's the strings conference. Oh, let me stop the